Welcome again to chemical reactor theory. So what we will do over the next few minutes is just recap what we have been doing so far, and I will also answer a couple of questions that have come this year, as well as one more question that was asked pretty much every year in the past. So frequently anticipated question, I guess. Okay, so what we talked about in the previous lecture is in this and the next module we are going to look at mechanisms. Mechanisms basically means how the reaction actually takes place. The most of the transformation do not happen in a single step, they involve multiple steps. So what those multiple steps are and how you can use the mechanism and make sense of it from the kinetic viewpoint is something that we are going to talk about in the next couple of modules. Okay, and the two things that we are going to look at quite a lot is one concept is the pseudo steady state concept. That pseudo steady state concept basically means that a species like an intermediate is in steady state. So even if the reaction is carried out in a transient reactor like a batch reactor, what happens is for a very large portion of the time, the concentration of intermediates are low and they do not change much with time. Okay. So, that is the concept that we are going to use in certain cases, and in certain other cases we are going to use the concept of partial equilibrium. What the idea of partial equilibrium is a particular reaction, it is not exactly in equilibrium, but it is approximately in equilibrium. Okay. What that means is that the rate of forward reaction is very closely matched by the rate of backward reaction. Okay. They are not equal. If they are equal, then this is equilibrium, but they are not very equal. So, for example, if the rate of forward reaction is 1000.1 and the rate of backward reaction is 1000, excuse me, the net rate of reaction is just 0.1. Okay. Why it is 0.1? Because the net rate is forward minus backward, but each forward and backward are very fast. The difference between them is what drives the overall reaction. Okay. So, we can use this in order to simplify the overall mechanism, and how we are going to do that is what we are going to talk about. Again, we will start with the case of an irreversible reaction. Before we do that, just a quick recap or just a couple of questions. One question was about collision theory and kinetic transition state theory. Okay, the idea of collision theory is basically, let us say we have a reaction, let us talk about the reaction A plus B going to products. So, in the reaction A plus B going to product, what happens in collision theory is, the idea is that the molecules of A and B, which are undergoing Brownian motion, will collide. Okay, at some point they will collide with each other. Okay. Now, the frequency of this collision is given by, this is the radius of the collision, square root of 8 kBt divided by pi multiplied by mu AB. So, mu AB is some kind of a molecular weight, okay, and 8 kBt, Kb is the Boltzmann constant. Boltzmann's constant is nothing but R in terms of molecules, okay, and T is the temperature. Okay. This multiplied by number density of A and B, which is basically molecules per unit volume. So, it is concentration multiplied by the Avogadro number. Okay, that is what Na and Nb is. Okay. And only some of these collisions are going to result in reaction. What collisions will result in the reaction? The collisions which are energetic enough. Okay. And the collisions, what collisions are energetic enough? They are those collisions that have energy greater than some kind of activation barrier. Okay. Yeah. Reduced mass, yes. So, it is kind of an average molecular weight. Yeah. Okay. So, if you look at this, This you can see this as some kind of a constant multiplied by t to the power half multiplied by e to the power minus e by RT. So, this is your pre-exponential factor. Okay. So, if you look at collision theory, the pre-exponential factor is proportional to t to the power, sorry, this is the rate constant. The pre-exponential factor is proportional to t to the power half. Okay. If you look at transition state theory, okay, and transition state theory comes from statistical mechanics. That is where our delta G dagger I had talked about. Okay. So, according to transition state theory, the rate constant K, okay, is given by KBT divided by H. KB is your Boltzmann constant, H is your Planck's constant. Okay. This guy multiplied by okay, which you can write this as e to the power okay, and this is nothing but this is exactly what we call as activation energy. So, this is your rate constant, sorry, not rate constant, pre-exponential factor. So, here the pre-exponential factor is basically some kind of a constant alpha, or we will call it beta t to the power 1 and you already know how the Arrhenius derivations are come about. Okay. So, if you look at the various theories, okay, to generalize all of this, we can write K as some pre-exponential factor t to the power beta this is the extended Arrhenius form. Okay. There was one of you who had come after the class last week and talked about the transition state theory. I had mentioned about the transition state theory that the pre-exponential is not proportional to temperature, which is not exactly true. That was a wrong statement. But essentially, whether it is collision theory, transition state theory, or just the vanilla Arrhenius equation, that all of them are subsumed in this more general form called the extended Arrhenius form. Okay. So, that is a quick word about the extended Arrhenius form. The other question was about equilibrium. When it comes to reactions, same reaction we can take as okay. So, delta G okay, this is how you get. So, basically at equilibrium, and let us say just for simplicity sake that this was a liquid phase reaction. It could be liquid, it could be gas, it doesn't really matter. Okay. So, we would be writing delta G naught okay, or we can therefore write this as e to the power minus delta G by RT, which we are going to represent as Kc is going to be equal to Cc Cd divided by CaCb. Okay. We divide throughout by Kc, okay, and take the rest of the expression to the left hand side. Then at equilibrium, we are going to have 1 minus 1 by Kc Cc Cd divided by Ca Cb equal to 0. Okay. Note that we have not brought in any kinetics at this point at all. Okay. At equilibrium, irrespective of the temperature, this needs to be satisfied. Okay. So, the rate expression that you derive, rate of forward minus rate of backward, okay, needs to satisfy eventually this particular expression. Okay. So, the shortcut that I am telling you right now, okay, again shortcuts basically means those are working solutions, those are not necessarily the entire truth. Okay. So, there might be situations where this will not come about. So, the shortcut that I am telling you is R net. You can, for the most part, at least for this course and for the most things that we do in research in this department, you will be able to write it as at this part. Okay. So, your R backward will somehow look like R forward divided by Kc Cc Cd. Okay. I have not written this as equal, I have written this as an equivalent sign. Okay. So, somehow when you rewrite your R backward, you should be able to rewrite it in approximately a form like this. Okay. What that means and so on, you will come to know over the course of next few weeks. Okay. All this is not truth, but shortcut. This one must be satisfied. Okay. This does not come, there is no kinetic aspect, nothing that we have brought in over here, this is coming only from thermodynamics. Okay. So, this is what I meant in the last couple of lectures when I said that this is what. So, the form of equation needs to be somehow matching this. Okay. What that means and so on, we will come to that over the next few weeks. Okay. So, but this is something that you need to kind of keep it at the back of your mind, not actively in your mind, please. Okay. Keeping it actively in your mind is basically going to, you will potentially make mistakes. You had a question? Yeah. For elementary reaction, none of you are going to have any problems. For elementary reaction, for example, the forward rate is KCA-CB, the backward rate is KB-CC-CD. There is absolutely no problem. If it was non-elementary with the forward rate being Kf, Ca to the power 0.6, Cb to the power 1.3, okay, what should be the backward rate? The backward rate, I think someone had said the backward rate was Kb multiplied by Cc to the power 0.5 Cd to the power something, right? No, it is not that, because that will not meet. If you rearrange it in this particular form, R net form, you will not get that. Okay. When you need to include thermodynamic constraint, you need to ensure that the form that you have indirectly reduces to this form, not necessarily always directly. Okay. So, the constraint that you need to meet basically is this constraint, right. This is thermodynamics, right. This is going to be or must be valid. Okay. Rate expressions are something that you have given, we have chosen, right. So, thermodynamics are also laws, but based on the laws all of the things come out. Okay. There might be exceptions in some cases. Thermodynamics laws do not yet have known exceptions. Okay. You are now getting into more complex domain. So, that is why I said it's a shortcut, right. So, the question was that do you always necessarily have to put it in this form? No, you do not necessarily have to put it in this form, okay. But essentially if this condition is not satisfied, okay, then you will have your system go to a different equilibrium conditions than what you will get if you were to solve a using thermodynamics. So, let us say these two rows I have given rate expressions, these two rows let us say your thermodynamics teacher for the same reaction has given you thermodynamics, okay. The reaction is the same, the reality is the same, okay. So, equilibrium that these two rows should get and the equilibrium conditions that these two rows should get should be the same, right, same within experimental conditions. So, maybe 1%, 2% error we will tolerate, not beyond that, okay. But if you are not careful about your rate expressions, the equilibrium that you will get might be say 15% conversion, the equilibrium that you would get might be 43% conversion, they are not the same, okay. And this equation is satisfied at all temperatures. The right hand side is independent of the temperature, the left hand side in this equation is the only one that depends on temperature, okay. So, the rate expression that you have when you write it in this form, that is one part that is dependent on temperature, other part that is not dependent on temperature. If this has to be valid at each time, this is the most convenient way to ensure that it is valid, okay. So, for most of the expression, no, all of the expressions that we are going to look at in this particular class, you will see that they will all turn out to be in some form reducible to this form, okay. But do not take this as, again, that is why I have written it very clearly over here, it is not truth but a shortcut, okay. So, yeah, let us move on, because so we can talk about this entire semester and you will still not be clear, and I know I was confused when I was a student, but now I can't put my head back to my student days and try to find out where exactly I was confused. So, yeah. Okay. So, we had considered this particular reaction, I do not know if it was A to I to P or A to B to C, okay. But so we had this equation, and from this equation when we solved ODE, we got an expression of this sort, okay. When we substituted this into this equation and then solved the ODE, so we will get what, dCi by dt is equal to K1 Ca0 e to the power minus K1 t minus K2 Ci. We take K2 Ci on to the other side, okay, and then we use the multiplicating factor. When we do that, the multiplicating factor is going to be e to the power K2t, okay. So, we will multiply throughout by e to the power minus K2t, do the integration and so on, and once you do that, your expression you are going to get is this, okay. So, in Excel we are going to take 3 different cases. We will say that we will say K1 is equal to 0, and we will take these and do this in Excel, okay. So, in Excel what we are going to do is we are going to write our time Ca, Ci, Cp, okay. We will take Ca naught equal to 1 for simplicity, okay. Take 0, 1, 2, 3, 4 and so on. You can take this and drag this, do it up to 20, okay. Ca naught is 1, we will just take that, okay. What is Ca? Ca is e to the power minus K1 t, So, equal to exp minus 0.1 into t. This is our CA. If you want to see how CA varies with time, just double click this and this will show the variation of CA with time. Okay. CI is basically going to be K1 CA naught divided by, so K1 divided by K2 minus K1, okay. So, equal to K1 is 0.1 divided by K2 minus K1, 1 minus 0.1, okay, multiplied by e to the power minus K1 t minus e to the power minus K2 t. T okay, this is CI and CP is just 1 minus CA minus CI. Okay. We can go to any of the rows and see, and click F2 and see whether the expression has been copied correctly or not, and we will just drag this. Okay. Now, let us say we wanted to change our values of K1, K2 and so on, right. So, we will write K1, oops, K is 0.1, okay. So, what we can do over here is we replace this with K1. Now, we can't actually drag this just directly. If you drag this, see, this is what is going to happen. Okay. Look at what has happened over here. We will click F2. Okay. Not only is, as you go down the row, not only is the T going down the row, but also K1 going down the row. We do not want K1 to go down the row. So, what we will do over here is we will put dollar sign. Okay. So, the rows are 1, 2, 3, 4, 5, the columns are A, B, C, D, E. So, we do not want this to move down the row, we do not want to move this along the column. So, we will put dollar and dollar at both places. And now, if we drag and drop, this is what you are going to get as it was before, right. So, our K1 does not change its location, K1 does not change its location. Same thing we will do over here wherever K1 is. So, this is where K1 is. I will put this guy and this, okay, 3 places I think, and again I will just put dollars. Wherever B1 was, I am replacing that with dollar $B $1. Okay. Now, I also want to do this with K2. So, K2 will be over here, value of K2 is 1, I will do the same. Okay. So, dollar $B $2, dollar $B $2. Okay. Now, if I drag and drop, okay, these values should not change. If they change, then that means I have done some mistake in the formula. Okay. Yeah. So, if you see this, these values have not changed. Okay. So, that means, yeah, we have done things probably right. Okay. Well, let us also, what we will do is, we will do rate of formation of A, rate of formation of I. Okay. What is rate of formation of A? It is minus 1 multiplied by K1 CA. RA is equal to okay. So this is what we are going to use. So K1 CA is RA equal to K1 multiplied by CA. Okay, I have to put dollars here. Should be negative of that, right? Okay, and RI. What is RI? RI is K1 multiplied by CA. So equal to K1 multiplied by CA minus K2 multiplied by CI. Again, I will put this dollars over here. Okay, and I have this net rate of RI. Okay. So now if you compare, the rate of A, formation of A and the rate of formation of I, okay, you will see that, okay, in this row the rates are comparable, in this row somewhat comparable, but essentially thereafter you will see that the rate of formation of I is almost one order of magnitude lower than rate of formation of A, rate of formation, yeah, or RI. Okay, what does that mean? This is exactly what you have talked about, what we have talked about as rate limiting step. Okay, what is the rate limiting step when you have K1 as 0.1 and K1 is 0.1 and K2 is 1, which one is rate limiting step? First one. What does that mean? That means that everything is governed by the first reaction. Okay, but a stronger concept that can be used. Rate limiting step is extremely useful concept. Okay, but in parallel with the rate limiting step, in order to reduce your mechanism and try to derive a rate expression, what we use, the next concept is that the pseudo steady state. Okay, what we will say is that I is in pseudo steady state, that means rate of formation, the net rate of formation of I is approximately 0, or after the initial time concentration of I does not change much. Okay. So now let us look at what is the concentration of I. Okay. Let us plot time versus concentration of all three concentrations. Insert, okay. So as you can see, this is the concentration of I and the concentration of I is very low, okay. That is because I is an intermediate. Let us say if our K2 was 10, what is going to happen? Even lower. Okay. The other thing that you see is K2 equal to 1 versus K2 equal to 10. What happened to product formation? See that? Very small change. Let us now make this 100, okay. I will press enter and then you watch what is happening. No change at all. Let us change it to 1000 and see what happens. Okay. The orange is going down, but there is no change in blue and grey. Okay. Let us go back and change it to say 100 or 10 is good enough for us. Okay. What will happen if I change from 0.1 to 0.2? Sorry? Curve of A will decrease. What about curve of product? What do you mean by it will decrease? It will decrease faster than what it is. What about product? Should lag a bit. Think about it. Rate limiting step. What do you think will happen? Chemistry folks also have done rate limiting step, right? Yeah, so it's not a concept that is new to us. Make a prediction. Okay, don't think about this. Be wrong. It's okay. I mean, if Sachin Tendulkar was afraid of getting bowled or Virat Kohli was afraid of getting bowled, they will never be a good batsman. Okay, think about what you know about rate limiting steps. Okay, first part of rate limiting step, hopefully it's aligned with what you are thinking. Okay, the really fast reaction, if I change the rate constant, the reactants and products concentrations are not going to be affected. The slow reaction, if I change, what's going to happen? Okay, so let's make this 0.2, right? The question that you have to ask yourself is this what you expected based on what you had learned about rate limiting steps? If not, you have only understood, you have only learned how to solve those equations. You have not really understood what it means, right? So, we will have to go back and rethink, various things that we have done. Okay. So, point 1, point 2. Let us make it a little bit different. So that it focuses only on the initial conditions. Okay. Let us see what happens with this. Much more significant. This is perhaps more aligned with what you are thinking, right? What about steady state? Or if you will wait for a really long time, if I make this say 1000, where will you eventually end up? Yes, if your time is 1000, all of A will go to 0, all of I will go to 0, the only thing that will be left will be C, right? Let us see what happens. Okay. So, we should not be doing that, let us do it like this. Okay. Essentially this is what you will get. Okay. Now, if you look at this, nothing will change. Now, if you maybe I should zoom it in. Okay. From here I change it to, so this was 0.1, right? Now, let us change it to 0.2. Okay. Just see what happens to the graph. What happened? No change. Let us change it to 0.4. No change. So, my question to you, what all you have been taught about rate limiting step, that is all nonsense? clearly R1 is the rate limiting step here, right? There are no two thoughts about it. A to I to P, A to I rate constant was 0.2, I to P rate constant is 100. But so the rate of reaction really depends only on K1, the slowest step. So I have doubled the slowest step, still you don't see anything happening. It means all the concepts that we have learned are wrong. Yes? No? That was the right answer. So the question is that really what is happening? So let's do this. So let's look at a reasonable time steps 1, 2, 3, 4, 5, 25 and so on, right. If this was 0.2, it's a pretty big change that you see in these columns, right. Just focus on this, it will not remain highlighted. So therefore you will have to keep your focus. I will do Control Z, see they are all changing. Okay. At steady state nothing is going to change. Okay. None of the things that you have learnt is wrong, we are looking at a wrong place. Okay. If you wait long enough in an irreversible reaction, everything will go to product. Okay. So whatever concepts that you have is kinetic concept, is how fast it goes to the product. Okay. One is running like a hare, other is running like a tortoise, all of them are going to reach finally the same condition. Okay. If you want to make it run like a tortoise, okay, it will go slower again. Now because I've plotted it differently, that's why you are seeing. If I had plotted it the same way as I had done earlier, you won't see it like this. Okay. But if I'm going very slow, again still I am reaching the same endpoint here. Here I am still reaching the same endpoint. Okay. If it's 0.1, again I am reaching the same endpoint. If it's 0.2, I am still reaching the same endpoint. Okay. But see how slowly I am going. So let us say you are looking at this tortoise and hare race. Okay. The race starts at 8 AM, you come 2 days later. Okay. You will not know whether hare won or tortoise won, both of them have reached their end point, right. One has reached slower, one has reached faster, does not matter. Okay. This is the example where the hare has learnt his lesson and therefore is not slept on the way. Okay. We will change the story slightly. Okay. So the question basically is about where you are going to probe. Okay. Same thing with equilibrium. If you wait for long enough time, CA, CB, CC, CD, they will end up being in equilibrium. The kinetics is about how fast you will reach, thermodynamics is about where you will end up. Okay. So that is the thing that you would want to note. So this is the sheet that we have already uploaded, and with K1, K2, with K1 equal to 0.1 and K2 equal to 0.1, 1 and 10, okay, the sheet which is already uploaded on Bitly website, the Google Drive, you can go and take a look at it. The most important items from that sheet I have listed over here. Okay. When K2 is 0.1, K2 is 1 or K2 is 10, this is what you are going to get. When K1 and K2 are matched, okay, you have a significant change in the concentration of I. Okay. At this case, I is not really an intermediate. Okay. You cannot use the next concept, that concept is of pseudo steady state. okay. But if, and this is how rate of I changes, okay. If you are looking at K1 equal to 0.1 and K2 equal to 1, okay, this is how the rate of I is going to change with time, okay. So, for this initial, for black thing, initial time approximately 2 time units, 2 minutes, the system is not under pseudo steady state, thereafter it is under pseudo steady state. When it comes to your red guy, this entire region system is under pseudo steady state. What we are going to do with pseudo steady state approximation is we will say that what happens in this region does not matter, okay, and hence we will use an approximation dCi by dt or Ri is approximately equal to 0, okay. So, to summarize, okay, which means let us see whether this is valid or not. Let us just make this more reasonable, okay. Okay. What is Ci approximation? Ci approximation is Ci is K2 by, sorry, K1 by K2, right. Okay, first point of course is going to be wrong. First is anyway initial point, so we are not going to use it anyway. Let us look at the error between Ci approximation and Ci. See how small the errors are compared to the value of Ci. So, Ci is 10 to the power minus 4, the error is 10 to the power minus 6, 2 orders of magnitude lower error, okay. So, if you compare, for example, let us just hide this, okay. Let us just compare Ci that you obtained by solving 2 equations versus Ci that you obtained by solving 1 equation, 1641, 1637, you will be happy with that? Yes, okay. 1343, 1341, will you be happy with that? 405, 404, would you be happy with that? Yeah. If you are saying no, then you should not be engineers. Okay, you may want to become physicists and look at what happens at quantum level. Okay, 331, 331, 271, 271, 222, 222, 182, 181, right. Now, let us look at the difference between, so dCA by dt equal to minus K1CA. Using PSS approximation, okay, and this one we had already obtained. Okay, remember how easy it was to solve this ODE compared to solving this ODE, right? If you think back 5 lectures before, okay, this ODE you have solved it multiple times. This ODE, the second ODE also, several of you have solved multiple times, but we still have to remember, integrating factors and all that, right. So, instead of solving the second ODE, what does PSS allow you to do? Replace ODE solving with just a simple algebraic equation solving. What do you lose? Hardly anything, right. You have not lost much. Your CA remains the same, your CI you have not lost much. CP is just CA naught minus CA naught e to the power minus A1t minus CA naught K1 by K2 e to the power minus K1t, okay, and you are done. Your CP gets calculated much easily compared to the previous case, okay. Now, this is where I will leave you with, and this is what we will start in the next class, and then we will jump on directly to Michaelis-Menten and the HBR. So, we will run tomorrow's class, the next class, in a pseudo what do you call tutorial mode, okay. We will take this example, A going to I going to P reversibly, both reactions are reversible. What you are going to try to do today is, can you write the ODEs down and solve them if you have all ODEs, okay. Unless you know how to do matrix calculus, these are not necessarily easy ODEs to solve, okay. Matrix calculus is fairly straightforward, okay. Anyone has done matrix calculus? Anyone has heard about matrix calculus? dx by or dy by dt equal to ky, where y is a vector and k is a matrix. That is essentially matrix calculus. It is essentially exactly going to be e to the power kt, just that exponential is a matrix exponent, okay. But anyway, so that is what we are going to start in the next class. We will take A going to I going to P, we are going to then take the examples from enzyme catalysis, and then we will do the example for HBR, okay.